So we'll begin, I suppose. Welcome back, and we are very happy to have Dr. Deep Ray from University of Southern California, and he actually graduated from TIFR Center for Applicable Mathematics in Bangalore, India. He was jointly advised by Praveen Chandrasekhar of TIFR-CAM and Professor Siddharth Mishra of CTH Zurich. And after that, he held a postdoctoral position at Rice University. And so now he is at University of Southern California, and he is going to talk on deep learning approaches for inverse problems. So over to you, Deep.
Thanks a lot. Thanks for the introduction. It's a pleasure to be here speaking at this workshop. Today I'll be talking about certain ways in which you can use these so-called deep learning techniques that become so popular nowadays. And I'll show you how you can use this in the context of solving inverse problems. And I guess what I will see how things proceed. I'll maybe take short breaks in the middle of the talk and see if there are any questions. And if there aren't none, I'll proceed forward. All right. I think before we get into the main part of the talk, I feel it's important to understand that these three terms, artificial intelligence, machine learning, and deep learning, which have become, part of our normal lingo these days, are at times used interchangeably. And it's important to understand that although these are three related concepts, there are differences between each of them. So if you ask the question, what is machine learning? Typically in machine learning, what you would do is you would collect some data, either from some phenomena you're observing, or maybe by solving some algorithm. And you could either end up with the data set S of points xi, of whatever quantity you're interested in, or maybe you get pairwise data xi, yi. So this could correspond to maybe some forward map that you're trying to approximate. So xi could be the input, yi could be the output. So say you have this data, then what you would do is you would choose some suitable machine learning algorithm and train it with the objective of discovering patterns or relations between these samples. And once you've trained this algorithm, then you would try to use this algorithm to make future predictions on new data points that you've not worked with while constructing the algorithm. So the simplest example is that of linear regression. So for instance, if these red points are your data points, and your task is in 2D to find a line that represents this data set well, that would be this blue line. And then if you're given a new X star, which you haven't seen, you would simply see what the value of the corresponding Y star is on that line, and that's your prediction. So this is linear regression. Then you could have a clustering problem where you're given a bunch of data points and you want to find clusters in which they belong. So in this case, what you can see is there are actually two clusters, and you want an algorithm that can figure out how to segregate data into different clusters. And then the task would be, if you're given a new, say, green point, the algorithm should tell you which cluster it belongs to. And finally, you could also have a problem where you're given a bunch of data points, say the one in reds, and you need an algorithm that can look at the data and understand what is the underlying distribution that is generating this data set. And once you learn this distribution, then the next task would be able to generate new points, say the one in green, from this learned distribution. So that's a generator. So this is what machine learning is. And there are many different algorithms in machine learning. You could use regression methods. You could use support vector machines, decision trees, k-mean clustering, and deep neural networks. So the point I'm trying to make here is that deep learning or deep neural networks is a type of algorithm consisting in this massive class of algorithms in machine learning. So deep learning is just a type of machine learning. So that's how you need to understand the relation between machine learning and deep learning. So that's for these two terms. What about artificial intelligence? So what is artificial intelligence? Well, it's basically trying to come up with a system which has human-like intelligence. So in principle, it is machine learning plus something more. So to understand this, let's look at this system for an AI self-driving car that, for instance, Tesla is really working hard to come up with. Of course, it's still not perfect, but this is the main idea. Let's say you have a car on which you have a camera that is mounted. And this camera is taking real-time images of the view ahead of the car. So say something like this. Then these images are sent to a machine learning algorithm that is doing semantic segmentation. So it's trying to look at this image and trying to figure out what type of objects are in front of the car at that point of time. And then it kind of color codes these different objects with different colors. So you could have cars or vehicles in blue, you could have the road in pink, you could have trees in green, and maybe in black you have human beings, right? So this part of taking an image and doing semantic segmentation is the machine learning algorithm. And that's where it ends. Once this segmentation is done, this data is sent to a decision system that is able to see the segmentation and figure out what it needs to do, whether it needs the car to slow down, speed up, turn left, turn right, or stop. And based on that decision, this decision is passed to a control module in the car, which finally takes the action of making the car take that particular action too, based on the image that it's seen. So in this entire system, which the entire thing is mimicking human-like intelligence, this is artificial intelligence, but machine learning is just a small part or a component of artificial intelligence. It's an important component, but it's just a component. So if you look at a Venn diagram, you have AI, which encompasses within machine learning techniques. And within machine learning techniques, you have deep learning, which is a specific type of machine learning algorithm that you can use. So with that out of the way, let's get to the main part of my talk. So here is an outline. So I will begin by introducing you to deep learning. And primarily, I'll be talking about multi-layer perceptron. This is the simplest kind of deep learning architecture that is there, that is used by people. And I will tell you what this architecture looks like, what are the various moving components of neural networks. And then I'll tell you about some convergence results that tell you how well these deep learning neural networks are able to approximate some target functions. Once we do that, I will go to another specific type or special type of deep learning architecture, which is known as generative adversarial networks. And what these generative adversarial networks can do is they can, from a particular set of data, learn the underlying distribution for that data set and then generate new samples from the distribution. And once I've done that, I will tell you how you can actually use GANs to solve inverse problems in the Bayesian framework. So I will first briefly introduce a Bayesian formulation for inverse problems, and then I'll show you two ways in which you can use GANs. One will be to use GANs to represent the prior in your Bayesian update step, and the next would be GANs to directly sample from the posterior. Now, depending on how things go, my plan would be to cover the first two sections in this first lecture, and section 3 I'll cover in the second part of the lecture. And depending on how much ground we are able to cover, I may or may not be able to cover GANs as posterior, but let's see how things go. All right, so let's begin with introduction to deep learning. Okay, so what we are actually trying to do with most neural networks is trying to approximate some unknown function. So say you have an unknown function f, which takes some input x, right? And gives you an output y. But of course, you don't know what this function is. All you know is this data set S, which gives you a bunch of x's for which you know the value of the function yi. So you have these pairwise data. Now the task is you want to be able to approximate f just based on this data set. Now you can use something like linear regression or other regression techniques, but this can become quite challenging to do if this is a highly nonlinear function. And what has been seen is neural networks actually do a pretty good job at approximating this function f. And in particular, you could actually make use of what is known as a multi-layer perceptron. So a multi-layer perceptron basically consists of artificial neurons, which are basic computing units in any neural network, which are stacked in a number of layers, stacked from left to right. So a multi-layer perceptron might have many layers. The first layer is known as the source layer, which simply provides an input to the network. So it doesn't do any computations. The last layer, which is known as the output layer, simply gives you a prediction y hat for some input x. And everything in the middle is known as hidden layers, right? And in each layer, each square that you see is one single artificial neuron that is doing some computations. Now, what is the computation that's going on inside each neuron? What it does is it receives the output of the previous layer. So let's say you're looking at the layer L. So it receives the output from the previous layer, and it takes a dot product with a weight matrix corresponding to that particular neuron, and it gives you a scalar value, and it adds a term B, which is known as the bias, and it sums the W dot X plus B, that's one scalar, and then it passes through an activation function. This is what happens inside a single neuron. Now, if you look at the entire layer L, then you can stack all these weights and form a weight matrix. You can stack each bias scalar for each neuron at the layer and get a bias vector. And the entire operation of an input XL minus 1 into the hidden layer L would simply be an affine transformation, which is acted upon by the weight matrix WL, and then you add the bias matrix BL. And once you've done that, then the output of this particular hidden layer is simply doing a component-wise application of this activation function. So you have an affine transformation followed by a component-wise activation of the corresponding vector that you get. Now, if you try to look at the entire action of the neural network from left to right, then you can actually rewrite the full neural network as simply a composition of alternating affine transformations and component-wise activations. So this is what a neural network really is. And here, theta would be all the weights and biases sitting in the entire neural network. And the idea would be to somehow find a way to choose these weights and biases of the whole network so that you're able to get a network that approximates your target function f as closely as possible. Okay, so this is what a multi-layer perceptron looks like. Now, what's important is to understand what these activation functions are, because this is very crucial in actually designing good neural networks. So let's look at some examples of activation functions. Okay, so I'm just showing you 6 activation functions. In principle, there are many out there, each with its own advantages and disadvantages. You could, for instance, simply take a linear activation function, okay? Or you could take something known as a rectified linear unit, which is piecewise linear, which is 0 when, say, xi is negative, and it's simply a linear with slope 1 when xi is positive. Or you have a modification of the rectified linear unit called a leaky ReLU, which has the same behavior when xi is positive, but has a small non-zero slope when xi is negative. Another popular one, which is a smooth activation, is the logistic function. So you note that this ReLU and leaky ReLU are not smooth because it's not differentiable at the origin. But the logistic function is nicely differentiable. And then you have a symmetric version of the logistic function, which is given by the tan hyperbolic function. And another activation function is simply the sine activation function. And this has recently become quite popular when it comes to using neural networks to approximate solutions to PDEs. And in practice, what people generally tend to use is the ReLU, leaky ReLU, or the sine activation functions. So these seem to work quite well. Now, here is a question to the audience.
So,
yeah.
Sorry, go ahead. I'll ask my question after your question.
Sure. So here's a question first. What do you think would happen if I use just the linear activation function in my entire neural network? If we look at this and go back to this expression over here, what would happen if I had all the activations being linear? What would that mean for the neural network? Maybe we have a response in the chat, or someone can say something.
Hello.
Hello.
Yeah. If we use the linear function, then we may have we may approximate only linear f. We may not be able to approximate if f is non-linear.
Correct. So if you take a linear activation, then essentially your entire neural network reduces to a single affine transformation, right? And that's not what we want, because if f is highly nonlinear, you would be in trouble. So the non-linearity of your activation function is actually what helps neural networks learn all sorts of complex structures and functions. And I think, Venki, you had a question, right?
Yeah, so any particular reason why or some oscillation type function plays a role in solutions to PDEs?
Well, you're talking about the sign activation function, right?
Correct.
Right. Actually, if you look at the sign activation function, if you use the sign activation function in this entire neural network, it's almost like you get some sort of a Fourier series approximation of functions. It's not really like a Fourier series because it's not a linear combination. It's non-linear composition of sign functions, but it almost gives you something like a Fourier series expansion. And that actually helps you learn functions if you have some regularity to the underlying solution. So this has been shown in a recent paper that this actually helps quite a bit in solving for PDEs.
I see. Okay, thanks.
All right. Okay. All right. So moving on. So these are what the activation functions look like. All right. So now coming back to the objectives, so we have some unknown function f. We are given this data set S, and we have this neural network. Then we have to train this network to approximate this function f. So what does that mean? So training requires you to first define some suitable loss function. Say you can take, in this case, maybe the mean square error, and you will take the mean square error loss over all the training samples, where you're trying to find the discrepancy between the true yi and the y that is being predicted by the neural network for the corresponding xi. And then this is a function of the trainable parameters, that's the weights and biases of the neural network. And to train the network, you have to solve the optimization problem, which minimizes this loss. And if you're able to find this theta star, that will lead to a neural network, which is, if it's trained correctly and this loss has gone sufficiently to low values, will give you a good enough approximation to any unknown function f that you're working with. And what is good about this optimization problems with neural networks is in the early 2000s, they discovered the use of an algorithm known as backpropagation, which mathematically is just applying the chain rule. And the way it works is that when you're trying to evaluate the network, you put an input on the left-hand side and you push all the way to the right to get the y hat. And when you're doing backpropagation and say using a gradient-based optimizer, you can actually pass the gradients from the right all the way back to the left. So you're propagating the gradients backwards in the neural network. And that's how this term backpropagation comes into play. It's a very efficient way of finding gradients of this loss function with respect to the weights and biases of the network. And that helps you train very fast and efficiently. Now, that's not the end of the story, because where you will typically spend the most amount of time in is to try and tune the network hyperparameters. And what are these hyperparameters? This would be, for instance, the width of each hidden layer. That is, how many neurons do you have in each hidden layer? It would be the depth, L, which is how many hidden layers do you have in your network? It would be the choice of the activation function, or what optimizer you want to use to solve this minimization problem. And when you're solving a minimization problem, there has to be some stopping criteria, because you will, of course, never go to machine precision 0. So what is your stopping criteria for this optimization process? Then what loss function must you use? So mean square error is one possibility, but you might have to use something else depending on the underlying problem. Another thing that's very important is regularization. And this ensures that your network does not overfit the training set. Because if you end up overfitting the training set, then there's a good chance that if you give it a new X, it will not give you a very good prediction. There are various techniques in regularizing your training and your network, so it gives you good predictions beyond your training set. And this is known as the network's ability to generalize. That's what it's called in machine learning lingo. And of course, you have to figure out how to suitably construct your training set or your data set to train on. And finally, which has apparently become very important these days, is you need to come up with a cool name for your neural network if you want to sell this network to the community. So if you are successful, you spent enough time and found all these hyperparameters and hence found a neural network that gives a good approximation to your F, you're in business.
So Deep, I have a question. So with respect to this, choosing these hyperparameters, right? So there is no, like, how do you go about choosing this? This is like trial and error? Or
no. So you basically are minimizing this loss function. And this loss function is a loss function in terms of these parameters, correct? So you would basically, if you're using, say, gradient descent, you will take the derivative of this loss function with respect to all the thetas. And then you will use that gradient to update your weights iteratively. So you could use a gradient-based method to solve this optimization problem, which is posed in terms of these trainable weights theta.
Correct, but then how about choosing the width or the depth and the intermediate steps, right? So those things.
Yeah, so that's hyperparameters. So maybe that I'll come to the next slide and I'll explain it. So here are some remarks. So there are parameters that
one more question.
Yeah.
This minimization method, square minimization or something like that.
Could you repeat that again?
Method is also based. Yeah, my question is related to how it is differ with the variational methods. We also did the optimizations using the least square methods. So means this is also the similar thing. We are minimizing using some kind of network, but in variational also we did minimizations. Yeah.
Sure.
So means is there any difference you can say?
Well, it depends. I mean, at the end, the reason why people tend to use gradient-based methods, right, is because it's very easy to evaluate gradients of the neural network using automatic differentiation, which is why these kind of methods are generally preferred for optimizing neural networks. But that doesn't mean you can't use another method if you want. But in variational method, it might be you'll have to figure out how to set up the problem for that particular scenario and see how to solve for thetas. If you think you can for a particular network architecture, you can.
Yeah, because in weather community, it is a big question that whether we continue the variational method or we need to go to the optimization through the deep learning. I asked this.
Yeah, well, I mean, I would say it really depends from problem to problem, and I would say that if I were to train, I would go with the normal deep learning route with gradient-based methods. That, in my experience, seems to work the best. Okay, maybe we can discuss a little bit more after the talk, and maybe I haven't completely understand your question correctly, but let's discuss after the lecture once. Okay, right. So here's the comment about having to find the hyperparameters. So typically, what you would do is you would split your data set into 3 types of data sets. The first one maybe is 80% of all samples in S will be called the training set, and that's what you use to find theta star. Then another 10% of the remainder of the set is known as a validation set, and that's what is used to tune the hyperparameters. So typically what you would do is you would have a training set which is used to optimize for the thetas, and then you would, at the while training, you would also try to see how the network is performing on the validation set. And if the validation error is not going down significantly, that means the hyperparameters that you've chosen is not working well beyond the training set. And this validation set is what's going to help you pick the corresponding hyperparameters. So it's almost like you have 2 loops. The inner loop is a normal optimization loop, while the outer one is almost like a hit and trial, or maybe using some kind of a grid-based approach where you figure out what hyperparameters you want to search over and try to find the hyperparameters that work best to give you good generalization errors. And finally, you will have a third data set, which is maybe the remaining 10% of S, which is the test set. And you will not touch this till the training and validation is done. Otherwise, you'll be data snooping, and that's not a good thing to do. The test set is the final thing where you will test and see how well your network works. So this is typically how you would go about training a network. So train to find theta star, validation to tune the hyperparameters, and the test set to finally see how well the network works on additional data. Does that answer your question? Thank you.
Yes, thanks.
All right. Okay. So first is that. The other one is, of course, that in principle, this mean square error function or any loss function can be highly nonlinear and non-convex. And that means could have multiple local optima. So what is advisable is that you first initialize your weights and you do your training, which is finding the optimal theta star. You get some value, you look at the validation error, then you retrain with a different initialization of theta and retrain. And each time you'll get a different network. And then you pick the network that actually ends up giving you, say, the lowest training error and the lowest validation error. And that's how you pick somehow the best network, and you're somewhat able to overcome this issue of having multiple local optima points. And what's also sometimes useful is, instead of training with the whole data set, so in some cases you might have 10,000 training samples, this becomes too big to handle at one go for each optimization step. So what's useful is to break up these training sets into small batches, and then you use these so-called mini batches to do one step of optimization. And you peruse through the entire training set by looking at all these mini batches chosen randomly. So this is how you typically train networks in practice. Now, multi-layer perceptrons are perhaps the simplest kind of network architecture that is available out there, but there are more sophisticated architectures that one can use. For instance, something called convolution neural networks, which is very useful when your data that you're trying to approximate or work with are images. So convolution neural networks are very useful for those kind of problems. Then you have something called residue neural networks. These are useful when you have to construct a network which is very deep. It makes sure that the network is still giving you robust results, even when the network is very deep. So the residual connections and residual networks are very useful for that. Then you have certain tasks where you have an image-to-image translation. So let's look at it in the context of, say, a PDE. Suppose you're solving a PDE in 2 dimensions, and you know the source term or the given data on the grid that can be seen as an image. And what you want to do is predict the solution, which is also on a grid. So these two, the input and the solution, can be seen as images, and you can actually use a UNet to go directly from the given data to the solution on that grid. So UNets are very useful for that. Then you have something called autoencoders, which are useful for doing dimension reduction. So it takes some big input and tries to reduce it and determine a small dimensional representation of your data set. And then that can be used for all sorts of reduced order modeling problems. And finally, another kind of network, which is the one I'll be talking about, is generative adversarial networks. And these are useful for learning distributions from a given data set. Okay, any questions thus far? I see there's something in the chat. How does it matter? How does the width and depth of the hidden layers matter? Well, there is actually results, and numerical and theoretical results, that show that it is better to have a deeper network versus having a wider network. Because think about it, the deeper you are, the more are the number of nonlinear transformations via the activation that you're applying. So the chances of you learning more complex features actually becomes more. So the expressibility of the network increases the deeper you go. But if you just go wide, you'll just be taking a linear combination of whatever is coming out of the layer for that activation function. So it is better. There are results to show you that going better leads to better approximations using neural networks. Okay, so let's proceed. Okay, so till now I've shown you, what I've shown you is the neural network can be used to approximate functions, but it'll also be good if you know how well they can approximate functions, or are they just nothing more than a black box? At least that's how they were initially designed. And the answer is there are, in fact, convergence results for neural networks when you're approximating functions. And there are many of them. I'll tell you about 3 important results, which is useful. And this also somehow relates to the width and the depth of the neural network. So reminding you again, the width would be how many neurons you have in each hidden layer, and depth would be how many hidden layers you have in your neural network. Okay, so here comes the first theorem. So we will consider multi-layer perceptrons, which have L hidden layers and have width H in each hidden layer. And we'll assume that K is some compact set on Rm. So the first theorem is by Pincus from 1999, where he says that if you consider scalar continuous functions on this compact set K, and you assume that your activation function sigma is continuous and non-polynomial, then for any epsilon that is given to you, you can find a neural network with just a single hidden layer that can approximate the underlying function f in the supremum norm within epsilon threshold. Okay, so this is a very nice result that tells you that single hidden layer neural networks are dense in the set of continuous functions defined on a compact set. correct? But there are two things about this network. First of all, it tells you that a single hidden layer is enough, but it does not tell you anything about what H would be, how wide must the network be. And there is no way of estimating that just based on this theorem. And of course, this theorem is also not constructive, so you won't actually get a way of constructing this neural network. It's just an existence theorem telling you you can find a neural network that gives you this kind of an approximation. Furthermore, it's asking us to use continuous non-polynomial activation functions. So of the 6 activation functions I showed you, all functions except the linear activation function would work in this particular setup. Okay, so this is the first theorem that's talking about density of neural networks with a single hidden layer in the space of scalar valued continuous functions on compact sets.
So Deep, I have a question. Like, what would be the method of proof? Because you said that there is no, it's not an existence. It's not a constructive proof. Is that correct?
No. Yeah, it's not a constructive proof. It's an existence proof. It uses functional analysis and measure theoretic analysis to be able to show this, and also some graph theory to show this. But the proof is still just an existence proof. It's like an approximation density proof that you have in many other scenarios. So you can't really construct a neural network explicitly that meets this criteria. But you can be shown with theorems and with various results that you can definitely find one somehow which meets this criteria. So typically the way you would solve this is you would have some approximations where you use triangle inequalities and you'll approximate intermediate terms, because you can approximate some of them with these kind of neural networks, and you'll end up with this overall epsilon approximation. Okay, so that's the first theorem. This is from 1999.
Thanks.
But now let's jump all the way to 2020. Okay, and now we have this theorem by Kidger and Lyons, where they look at continuous functions, but now they're looking at vector valued functions, and they're assuming that your activation function should be non-affine, continuous, and should be continuously differentiable at some point in the domain. And at that point, the derivative should be non-zero. So if you have such an activation function, then for any given epsilon, you can find a neural network whose width is m plus n plus 2, where m is the input dimension, n is the output dimension, such that it approximates the underlying function up to epsilon approximation in a supernorm. Here, first of all, this result holds for vector valued functions. That's pretty nice. Now, while in this case, we have a bound for h, so we know how wide the network must be. Unfortunately, in this case, we don't have a bound on L. Okay, so again, if you don't have a bound on both h and L, you don't really have any bound on how large a network you actually need to approximate this F. And once again, all the activation functions except the linear activation function would work in this scenario. Okay. All right, any questions on this? Okay, and now let's come to the last and most recent theorem, which came out just earlier this year.
This L is the number of hidden layers, or what is that?
Which one? M?
L.
M.
L.
Capital L. L is the number of hidden layers. L is the number of hidden layers. Yes. So how deep is your network, basically?
And we cannot. We are not giving any bound on L or something like that. I mean, how this
No.
L?
Yeah, you're saying that you can find an L depending on epsilon and F, but you don't know how big or small this L will be. You don't have a way of estimating it.
Okay.
But since we can't bound H and L till now, this theorem from 2021 can actually give you those bounds. So here it was shown that if F is a Helder continuous function with exponents P and alpha, and you define R to be simply P plus alpha, then you can show that there exists a neural network with the ReLU activation function, right? You remember the ReLU activation function, which looks like this, right? Is piecewise linear. So with the ReLU activation function, you can find a neural network which has width 2m plus 10, where m again is the input dimension, and you assume that n is the total number of trainable parameters, right? So if you have the total number of trainable parameters n, that puts a bound on how big the network can be. So with this h and with this n, you can bound the approximation error of f by some constant that depends on r and m, and by this term, which is log n over n to the power 2 over r over m. Okay. So you have this error estimate. And the nice thing about this is, first of all, you already have a bound on H. Now, if you want this error to be less than some epsilon, then you can actually find an L that depends on this epsilon. So you have an exact bound on N because you're able to first, you know that N is given to you. That's the total number of parameters. You have epsilon given to you. Then based on that and based on H, you can find what the depth of the network needs to be to actually get an epsilon approximation of your neural network. So with this theorem, you actually have a bound on both the H and the L, given a particular epsilon. And two things to note here is because of the exponent over here, if R increases, that means your function is smoother than the irregularity of the function increases. So as the regularity of the function increases, this term over here will decrease. So you have better errors, or smaller errors for more regular functions. On the other hand, M over here, which is the input dimension, if M increases, that means you're approximating functions defined on a very high dimensional input domain, then you'll need to actually come up with a much larger network to reduce your approximation error. And another theorem, which I'm not stating here and is also there in Yarotsky's paper, is he shows if you use not just the ReLU function, but you use the ReLU activation along with the sign activation, you can actually replace this logarithmic error bound with an exponential decay in terms of N, right? So, and this kind of answers one of the questions that you asked, Venki, what is one of the advantages of sign activation? Here with sign activation, you can actually show exponential convergence if used in a smart way.
I see. And I suppose this again is not a constructive proof. This is an existence.
Yes, again, an existence proof, yes.
I see.
Okay, but what these theorems generally tell you is they may not tell you how to construct neural networks, but they'll give you an idea of how large a neural network you might need to use to approximate your function. So the term is guiding principles. So that's how I would say you would use these theorems. Okay. All right,
Hello?
any more questions? Yeah.
Yeah, can we not use theorem 1 and theorem 2 to get bounds for both L and H in the case of N is equal to 1?
No, because I don't think it may be easy to do that because there are different conditions on the activation functions of that, right? In one case, it's a non-polynomial function. Here, you have a different condition of sigma. So perhaps in very simple cases, you might be able to get it. But for a general function, you might not be able to. And secondly, this theorem is defined for, vector valued functions. So perhaps in simplistic cases, you might be able to get something, but not for general functions in general. Okay, all right. So that's about convergence results of multilayer perceptrons. And now let me come to something known as generative adversarial networks. Okay, and we'll be changing tracks here. Till now, we were looking at neural networks to approximate functions, so essentially doing function regression. Now we'll come into the domain of probabilities, where you're trying to understand the underlying probability distribution of some data set. Okay, and this is where GANs come into play. Okay, so say we are interested in generating samples from a probability distribution. So if you're given a data set S of some points xi, some finite set, and you know this comes from some underlying distribution Px, which you don't know, then the goal would be to discover the underlying distribution Px from this data set S. And after that, generate new samples from this distribution, okay? Now, if you're given points like this, say if you're given points in R2, which look like this, okay? You can see by looking at it that this seems to be a uniform spread of points. So you could make a uniform prior assumption of the distribution and perhaps find the parameters and figure out what the underlying distribution is. And then using inbuilt pseudo-random generators for uniform distribution, you can create new samples. On the other hand, if you have points like this, which seem to be clustered at some point and then radially they become sparse, then a normal distribution or Gaussian distribution would be a good prior for something like this. So you would have this prior and then maybe find the corresponding mean and covariance matrix that best describes this data set. Okay. So you can do this for samples like this and that. And once you found the distribution, you can generate new samples from it. That's not a problem. Now, what if you're given samples which look like this? So suppose your samples are n cross n images. So they could be, for instance, something like this, which describes this binary phase microstructure, which has a value in the black zone and value in the yellow zone. So say you have samples like this, or you have samples which correspond to handwritten digits. These are known as MNIST digits in machine learning. Or for people in this conference workshop, I'm sure you might have seen this. This is the Shep-Logan phantom, which is used for solving inverse radon transform problems, which approximates the human head. So this is what your images look like. Then how would you actually represent this using some prior? You won't be able to use a Gaussian prior to approximate this, because this is very, very complex to simply represent by a Gaussian. So how would you do this? And this is kind of where the so-called data-driven generative algorithms come into play, which are able to look at these complex data samples and understand the underlying distribution and generate new samples of this type. And there are quite a few out there, and the one that I'm talking about today is the generative adversarial neural networks. Okay, so the task is to see this data set and try to generate new samples which look just like this. Correct? Any questions on this? Okay, so let's see what.
So,
yeah.
So Deep, if I understand it correctly, it is to generate more data from limited data. Is that correct?
Yes. So if you're given a data set S and you want to say, use this to discover the underlying distribution and create new samples of this type, that is the task. So how do you do that if you're only given a finite number of samples and you don't know the explicit expression of P?
I see. But the potential application could be like where you have like very limited sample set, and then you want to generate more sample sets so that your algorithm becomes better. Is that correct?
That's one application, but of course, it really depends on the kind of algorithm you're using. GANs primarily are actually very data hungry, so they need quite a few samples. But many problems, they have been used in many applications where you can augment the small data set that you have and then use that to train on, and it still works very well. But yeah, essentially it will work in scenarios where you have limited data and you want to be able to generate more samples of the same type for some application. And we'll see two applications today where you can use that effectively.
Okay.
All right, so let's come to generative adversarial networks. So these were designed by Goodfellow and his authors his co-authors in 2014. And they were designed primarily to learn and sample from some target distribution Px, which is not known a priori. Okay, and although it's called a generative adversarial network, it actually comprises of not one, but it comprises two neural networks. Okay, so it has one network called the generator G, and another network called the critic, which are represented by D. And this G and D could have whatever architecture you want. It could be multi-layer perceptrons, it could be convolution neural networks, it could be U-nets, whatever you like it to be. But the point is that there are two networks, G and D, that you have to work with. Now let's look into what the role of each of these networks is. So let's look at the generator first. Okay, so the generator can actually be seen like a fugitive or someone who's trying to generate counterfeit money. So the generator is a network which has its trainable parameters theta, and its job is to generate fake samples x tilde. It's a function which is defined from omega z to omega x. So it takes in a latent variable z, which is in an nz dimensional space. And typically, z is sampled from some simple distribution, like a multivariate Gaussian distribution. Okay, so you have the z, which is going into the generator, and is giving you an x tilde, which is supposed to be a fake sample from the target distribution. And what is important is typically the dimension of z, which is the input of the generator, is much, much, much smaller than the dimension of x. So the dimension of x could be something like 3 million. but the dimension of Z could be of the order of 100. Okay, so you also have a low order representation or low dimension representation of X tilde. So the generator is trying to generate fake samples. Okay, so it's creating counterfeit money. Now, what does the critic do? The critic is like a cop. It's trying to figure out and distinguish which notes are fake and which notes are real. Okay, so it's another network which has its own tradable parameters phi, and it takes in an input from the domain omega x. And what it does is the following: whenever it sees a sample from the true distribution, it takes a very large value. But whenever it sees a sample not from the true distribution, it takes a very low value. So it's using the value of the D can be used to distinguish between fake and real samples. And what typically happens is that the generator is trying to create samples to fool the critic, while the critic is trying to up its game and figure out how to catch fake samples. So they're kind of trained to battle each other, and that is why they call adversarial networks, right? They're adversaries of each other. So is this part clear? Any questions on this?
Hi, Deep.
Yeah.
Yeah, so if I understand it correctly, then you first generate fake data, and then you go through the critic, and then again you update the generator, or you work with the same generator?
Yeah, so I will tell you the exact algorithm as to how you would do this training, because you would train them simultaneously. So,
yeah, okay.
So I'll get to that answer in a bit. Okay. All right. So yeah, go ahead.
Yeah, Deep, question here. So is this approach is not similar to the particle filter?
To the
particle filter?
Particle filter. Yeah, you could say it's somewhat like that. It says similarities, right?
Yes.
Yeah. So you could say there are similarities in the way you would do that as well, right? Yes. Okay. So anyway, so to train the generator and the critic, we need to define a suitable loss function. Okay. And what should be the loss function here? So you pick some metric defined on the space of probability measures on omega x. Okay. And you set the loss function, which I'm writing as pi of GD, which in principle is a loss function in terms of the trainable weights of both networks, as the metric, which is finding the distance between the true distribution and the fake distribution, which is nothing but the push forward of the measure PZ by the generator. Okay, so this metric is measuring the discrepancy between the true distribution and the generated distribution. And what the generator tries to do is the generator will try to minimize this loss function because it wants to create samples as close to the true distribution, while the critic is going to try and increase this loss function because it wants to distinguish or pull apart fake and real distributions. So in principle, you'll actually be solving a min-max problem where the critic is maximizing this loss and the generator is minimizing this loss. So hence it's also called adversarial training. And this is how you would actually try to find the G star and D star that somehow tries to find a saddle point for this loss function. Okay. And depending on what metric M you choose, you will get a different kind of generator, as it will describe how PX kind of converges to the fake. The fake distribution converges to the underlying true distribution. Okay, and I will be looking at a very specific kind of metric, which is known as the Wasserstein-1 metric, right? And I'll be looking at what it's called as the Wasserstein gap. And this was proposed by Arjovsky et al. In 2017, where they make use of the Wasserstein-1 metric. And just to remind you what the Wasserstein-1 metric looks like, the Wasserstein-1 metric between two distributions P1 and P2 is going to be the infimum overall joint distributions such that whose marginals are P1 and P2. And you're taking an infimum of the expectation of the L1 distance between X1 and X2, where X1 and X2 are sampled from these joint distributions. Okay, so this is the Wasserstein metric. It appears a lot in optimal transport problems. But unfortunately, this infimum formulation is not very easy to work with. Now, fortunately, there is a dual characterization, or the Kantorowicz-Rubinstein dual characterization of the Wasserstein-1 metric, that says that the Wallerstein distance between P1 and P2 can be seen as the supremum of this quantity in the brackets over all F, which are Lipschitz, with Lipschitz constant less than or equal to 1. And it's taking a supremum of the expectation of F evaluated over true samples minus the expectation of F evaluated over not true. In this case, it's the distribution P1 minus the expectation of F evaluated over the distribution P2. Okay, so this is the dual characterization of the Wallerstein metric. Now, keeping this in mind, we define the loss function for our Wallerstein GAN, which looks essentially the same as what's inside the bracket for the Wallerstein distance, right? So it's the expectation of the value of the critic where X is sampled from the true distribution minus the expectation of D of G of Z, where Z is sampled from PZ. So this is essentially what is creating the fake distributions. So it's trying to look at the difference between the expectation of a real samples and the expectation of the fake samples as evaluated through the critic. Now, under the constraint that D is Lipschitz 1, you can actually first maximize this loss function. So, right, so you maximize overall D under this constraint. And what you will see is this actually corresponds to obtaining the Wallerstein 1 distance between the distribution Px, which is the true distribution, and the push forward of Pz through the generator G. So you find a D star for a fixed G. And then once you found this D star, you find the optimal G star by doing a minimization of the Wallerstein metric. So in principle, by solving the min-max problem with this particular objective function, what the optimal generator is doing is it's minimizing the Wallerstein 1 metric between the fake distribution and the true distribution. And what is also known about the Wallerstein 1 metric is that if you can show that if this loss function goes to 0, that means you converge in the Wallerstein 1 metric. This is equivalent to convergence in the weak sense for measures. And weak convergence for measures basically means that the expectation of L of X, where X is sampled from the true distribution, is the same as expectation of L of G star, the optimal G of Z, where Z is sampled from PZ, for all L, which is continuous and bounded in omega X. In other words, your moments converge for the true distribution and the fake distribution. So if you take L to be simply simply to be identity, your means would match. If you take L to be L squared, the quadratic function, your second moments will converge. Then with that, you can show that the standard deviation converges, and so on and so forth. So if you're able to find a G star that sends the loss function to 0, you have W1 convergence, you have weak convergence, and you'll be guaranteed that the moments of the true and the fake distributions converge. Okay, any questions on this?
Yeah, I have one question.
Yeah.
So if distribution are changes with time, suppose priori is Gaussian, but posteriori is not Gaussian, then critics will not allow that to include the extreme values in this case.
Repeat that again. You're saying that if what is Gaussian? Can you repeat your question? Comment again, please.
Yeah, that means if my distributions are changes with time. Suppose my priori distribution is Gaussian, but posteriori is not Gaussian. Then then within this, the critics will not allow the extreme values in the distributions.
Okay, I'm not sure why that's the case, because you're not assuming anything about what kind of distribution there is for the posterior or prior.
Yeah, we in some cases we have that, means the priori distribution is Gaussian, but once the model is simulated with time, the posteriori is not Gaussian. Okay. So in that case, this critics, because critics take the fixed distribution, so every time they take the samples from the same Gaussian distribution only. Yeah.
No, the critic is not taking samples from the same Gaussian distribution. The critic will be taking samples from the fake or the real distribution, whichever one it is, right?
The critic, but every time, every time he select only the samples which are assumed from the same distribution.
I don't think I completely follow. But let's get we can discuss this after the lecture again. I would like to come back to this and discuss this point. Maybe I'm not completely understanding it again. right? Okay, but let's talk about this more. All right. Okay, so this is the Wallerstein GAN. Of course, in practice, you can't, solve D all the way to the optimality and then find G star. It's not computationally tractable. In practice, you have to do the following thing. First of all, you don't really know the true distribution. All you have is the values of X from the true distribution, but this is only a finite data set S. That's all you know about the true distribution. So this is what you have to work with. So what you do is, first of all the expectations over here have to be replaced by Monte Carlo averages, right? So the expectation of D of X will simply be 1 over n summation of D xi's, where xi's are all the training points. And similarly, the expectation of D of G of Z will be represented by Monte Carlo average, where each Zi will be sampled from the Gaussian distribution that you're generating from, okay? And then to solve this min-max problem, since you can't solve the discriminator all the way to optima, what you would do is you would take n steps of optimization for the critic, fixing the generator, and then you will fix that particular critic and take one step of optimization for the generator. So you will iteratively solve for the critic and the generator by taking n steps for the critic and then taking one step for the generator. And this is what is done in practice to train all sorts of GANs, and it works well. And additionally, if you remember that I said that we have to work under the constraint that the critic has to be Lipschitz 1, I won't get into details, but there are ways of actually augmenting the loss function with a gradient penalty term. This was devised by Gulrajani in 2017, where you have a constraint like this, where you're constraining the norm of the gradient of the critic with respect to its input, and you're constraining it to be close to 1. So you add this penalty term to your loss when you're updating the critic, and this helps control the Lipschitz 1 constant for the critic. Okay, and I quickly like to show you what you can actually do with a GAN. All right, so this is one example from this group from NVIDIA, which is Karas et al. This is from a paper from 2018, which is already quite a dated paper. So in the field of machine learning, something that's even a year old is considered to be dated, unfortunately. That's how fast-paced this domain is. But what they did is they looked at, they want to train a GAN on a bunch of images which are taken from this data set called Celeb AHQ, which is high quality images of celebrities. And they want to generate new celebrity faces once the network is trained, okay? So over here, the first 4 rows are samples from the training set, which was used to generate the GAN. And on the last row, once the GAN is trained, they just simply sampled Z from a Gaussian distribution. And those were the images that the GAN generated. So they actually look very similar to other celebrity images. Okay, so the GAN is able to do quite a good job. Now, 2 things to note. First of all, the dimension NX of each image is 1024 cross 1024 cross 3, because it's a RGB, it's a colored image that has 3 channels, and in each channel it's a 1024 cross 1024. So dimension of NX is more than 3 million, but the dimension of NZ was only taken to be 512. So you have a massive dimension reduction, where by only sampling something in a 512 dimensional space, you're able to represent something which has got a dimension of 3 million or more. And secondly, a GAN doesn't always get everything correct. So for instance, if you look at this particular image, you see that the GAN has decided to put a earring on the left ear, but has nicely forgotten to put a earring on the right ear, okay? So it doesn't get everything correct, but overall, it seems to have qualitatively the same kind of images that he wanted to generate to begin with, okay? So this is the kind of strength that, that GANs have in generating new samples by just working on some training set to begin with. Okay, so let me stop here, and I can take more questions of what I've discussed, and then I can continue with the rest in the next lecture. So are there any questions? Well, it seems no. So is everything clear? I mean, the potential of what GANs can do in the context of Bayesian inference will be very clear in the next part of the lecture, but we'll get to that in the next lecture.
Okay, so if no more questions, then we'll take a break for half an hour, and so we'll come back at. Okay, so people are in different time zones, but anyway, half an hour is the same for everybody. So
right.
So we'll rejoin in half an hour.
Sure. I mean, I can still hang around if anyone has any other lingering questions that weren't answered. I'll be happy to stay back and discuss a bit if anyone else has any questions. I know there were a few which I wasn't able to answer in the during the lecture, but I'll be happy to answer them now if they would like to stay back and discuss.
Yeah, Deep, thank you. Actually, Prashant here. So actually, I am mainly a person on working this weather-related activities. So actually, in weather prediction problems, now people are largely focused on deep learning and this thing. So that's why I have some questions related to, because we already use a huge number of techniques like variational method, and in last you saw some Markov chain, and we use the Markov chain Monte Carlo. We also called that as a particle filter type of method. But what I found that the techniques which you show in the GAN, they are somehow motivated from these techniques, like the particle filter. In particle filter also we did a similar thing. We generate so many samples which we called as a particles or ensembles, and then we gave the weight to each particle and try to get the Postry distributions. So is it not very similar to the existing techniques?
I mean, in some sense, yes and no. I mean, it is similar in the sense that you're training it, you're using data to kind of figure out what the posterior is. I guess the difference would be primarily in the fact that the kind of functions you're trying to use to approximate the priors, the posterior, is somewhat different, right? So the structure of a network is very different, and since it comes from the computer vision domain, they're at times actually able to capture a lot of these nice features which our traditional methods may not be able to capture. So in terms of capturing features and doing feature selection, neural networks work well. But of course, there is no guarantee that it'll always work well. Sometimes traditional methods still work better than deep learning. So deep learning is by no means the holy grail. It will not solve every single problem, but there are similarities between how you would train certain deep learning techniques and how you would even say do some variation inference and variation-based methods otherwise.
Okay, and then another the well-known theory in our field is that because in ECMWF also people are thinking of that, because there are two parallel approaches. One is the minimization using the standard techniques like variational I told, and then now people are working a lot on the minimization using the neural network and these deep learning. So but somehow the basic background of using the minimization of cost function and those things are almost similar in both the methods.
So when you say minimization using deep learning, what exactly do you mean? You mean that you're minimizing a deep learning operator, or you're using a deep learning network to help you with minimizing something else?
No. Actually, we have a cost function where we have a two different set of observations. One is the some satellite observation, another is form model. Then we try to find a best fit from these two observations. So that is a cost function based on the observation and model input. So that data we want to minimize.
I see. And what you're saying is, you're still there? I think you're stuck. Prashant? Oops, I think we lost him. Yeah, Prashant, can you hear me? You're muted right now.
Yes, sorry.
Yeah.
So now people are working on that, means in place of using that traditional method of minimization, people are working on that how deep learning type of technique can be used for minimization.
Okay.
So yeah.
Basically using automatic differentiations. Essentially what is being used in deep learning is automatic differentiation and backpropagation.
Yes.
And automatic differentiation
Yes,
has been used for a long time for even solving adjoint problems for optimization, right? They've been around for a while, yes.
Yes, because in the existing techniques we have an issue that we cannot write adjoint code for each forward model. So that's why people think that means this may be a better choice.
Yeah, I can imagine, because and I guess it becomes easier with 1 second. I'm not really able to share. Yeah, so I guess so I guess with neural networks you can actually do automatic differentiation very easily because of the way the network is structured. Because you can backpropagate the gradients very easily, and that's also because there's this repetitive recursive structure to the neural network, and you can do that very nicely. But if you don't have this recursive structure, then it becomes a little more challenging to propagate things backwards. But it can be done if you have things set up. If you're allowed to take, almost like the chain rule type backpropagation or automatic differentiation of various inbuilt functions. I think that as long as you can find the automatic derivatives, it should work just as well.
Okay. And one more thing is that, is there any limitation that if suppose going forward and backward, my distribution is changes? So whether it's there is any limit on that?
Distribution changes in the sense in a GAN?
Yeah, because means suppose in my model when we go forward. Means the original distribution is changes with time. So whether it's have any influence on your this type of technique?
Well, I mean, then you will basically be training the stuff on a particular kind of distribution. Now, if the distribution itself changes, then the chances are that the same network will not work well because it's been trained to work on a very specific kind of distribution. If the distribution is evolved, you're basically trying to ask if you'll almost asking the question if it will work well for out of distribution samples, and if the distribution is changed quite a bit. In that case, it isn't guaranteed that it will work if it's changed quite a bit. In that case, you might just have to retrain the network from scratch. I know that there are people who are using a GAN iteratively in solving data assimilation problems, where they first solve it for some prior, they make an update, and they come back and update the GAN again. But in that case, you'll have to keep updating the GAN repeatedly if your distribution is evolving. Unless you have a way of parametrizing how your distribution is evolving, and that parameter can also be sent in as an input to the GAN. So the GAN then learns on a larger parameterized set of distributions instead of just a distribution at some time instance, and then it can actually work better for more samples from a larger broad distribution.
Yes. I think I got you my answer. Because now people are because in weather we have a problem like that, means because the cloud is evolving and changing every time step. So those type of problems are there. So I thank you, Deep. Actually, I got my answer.
Otherwise, even if things are changing, if you can still find some inherent underlying distribution that remains the same, you can perhaps just work with that and see if things still work better, right? I mean, there'll be some elements that remain the same, even if clouds are moving. Maybe there's some distribution. I mean, of course, if you're looking at there being clouds and there being a clear sky, when they're a completely different distribution.
But sometimes, cloud is evolving and dissipating. So many processes are there. So okay.
Okay.
Thank you, Deep.
You're most welcome.